Next, we're going to talk about making inferences associated with our regression model. There's going to be a few different kinds of inferences that we want to make. And the first one is with respect to our beta 1 here. Is this beta 1 equal to 0 or not? And the reason is kind of obvious through taking a look at a regression model. So our regression model is y is equal to beta 0 plus beta 1 times x plus epsilon. This is the model in the population itself. And look what happens when beta 1 is equal to 0. 0 times x, of course, is 0. So essentially, x falls out. So what this model now is saying is that no matter what x is, y is not going to change. So if we want to know if there's a relationship between x and y, we want to look at this beta 1. If the beta 1 is equal to 0, it says there's not a linear relationship. If beta 1 does not equal 0, it says, yes, indeed, there is some kind of relationship there. So, for example, let's say that beta 0 is equal to 3 in this corresponding model. Then if I were to plot now the expected value of y is equal to 3 plus 0 times x, well, what do we have? Just a flat line at y equals 3, or at 3 at the y-axis there. And so we can see that no matter what x is, the line doesn't change. And the blue dots here represent the scattering of observations that would exist in our population if we somehow knew all the particular points. And we can see that there's really no relationship between x and y with these points and then the line. Okay. So we want to make inferences about beta 1. Now, one can show, similar to how we had, let's say, y bar minus mu over s times, or s divided by the square root of n. Another way that you could write this is like this, which we really didn't focus on. If you remember, we had y bar minus mu divided by the square root of an estimate of the variance for y bar. Well, we can do the same thing here. Beta hat 1 minus beta 1 divided by the square root of the estimated variance of beta hat 1. Very similar like quantity. Before, when we were working with y bar, this had a corresponding t distribution to it with n minus 1 degrees of freedom, where n was our sample size. Now, this particular quantity here, if we think of beta hat 1 actually as a random variable, this also has a t distribution, ends up having n minus 2 degrees of freedom. This minus 2, without going into all the details, comes about because we're trying to estimate beta hat 0 and also beta hat 1. Okay, well, what is this estimated variance, though? Again, in a mathematical statistics course, one could actually derive what it is, and this is what it looks like. S squared sub epsilon, so our estimate of sigma squared epsilon, remember the variance of epsilon is sigma squared epsilon, and then we divide by the sum of all of our x's, subtract off the corresponding mean of the x's, square it. So we have this quantity that has a t distribution, and very similarly to what we've done now many times before in this particular course, we're going to put this quantity that has a particular distribution with it in the middle of a probability statement, where on the edges of that probability statement, one could say, we're going to have quantiles of this corresponding distribution for the thing that's in the middle. We choose then the corresponding quantiles in a way such that the whole probability statement, the whole probability has a probability of 1 minus alpha. Okay? Once we get that statement, we again do some algebra so we get our parameter of interest to be only in the middle itself. So that now beta 1's in the middle. I got something on the left, something on the right, and the only difference is a minus and a plus there. Then, if we think of now beta hat 1 now in terms of the actual observed value that you can get from calculated in a sample, we can now write out what our confidence interval for beta 1 would be. So it's beta hat 1 minus a quantile from the t distribution times the square root of the estimated variance of beta hat 1. That's the lower bound. Upper bound's exactly the same, but we put a plus there instead. So with this confidence interval, we could do a hypothesis test for beta 1 is equal to 0. Step 1, with the confidence interval method, we state our hypotheses. Notice what beta 1 equals 0 means. It means that there's no linear relationship. Beta 1 does not equal 0. It means, yeah, there is some kind of linear relationship that's going on there. Now, you don't need to actually write this part out here yourself. It's okay if you just said beta 1 equals 0 versus beta 1 does not equal 0. Step 2, we calculate our confidence interval. Step 3, we check, is 0 in the interval? And if it is, we don't reject HO. If it isn't, we reject HO. And then step 4, what does this mean in terms of the original problem itself? Well, if we reject HO, that says, well, beta 1 does not equal 0. That means there is sufficient evidence to show that X is linearly related to Y. Okay, if we don't reject HO, well, based upon our sample itself, there isn't sufficient evidence to say, yeah, I feel very, very good about this, that there is a linear relationship. You know, we're not able to say it from this particular sample. Of course, we could do the hypothesis test with the test statistic method as well. Hypotheses are the same. Our test statistic, well, we take that t quantity that we saw before, and we simply replace that beta 1 there with our hypothesized value under the null hypothesis. Step 3, we find our critical value from the t distribution. There's actually it's a two-tailed test, so there's 2 critical values. Notice the degrees of freedom there. Step 4, we decide if we reject or don't reject, so we can do our little plot. If my test statistic falls anywhere on the extreme part of the distribution where there's very little probability of being out there, if the null hypothesis was true, if I would have a test statistic out there that would say, hey, something's weird going on here, because if the null hypothesis was true, this would be very unusual to happen. So therefore, reject HO. Otherwise, if we're somewhere in between the 2 critical values, don't reject HO. In step 5, state the conclusion in terms of the original problem itself. And lastly, with the p-value method, we calculate our p-value much the same way as we would before. 2 times the probability of random variable t is greater than the absolute value of our test statistic. Then we check, is the p-value small or not relative to alpha? If it is, reject. If it isn't, don't reject. And then the rest of the hypothesis test proceeds as usual. Okay, so let's take a look at an example. This goes back to our sales and advertising example from before. We're going to use alpha 0.05 here. Well, first of all, what are we trying to do here? We're interested to see, is advertising linear related to sales? If it is, and if you're, let's say, someone who's working in the company, then you think, okay, I can use advertising to predict what sales is. If we can't say that, yes, indeed, there is a relationship, then you might want to say, hold on here. I think maybe something else is going on here that's affecting sales, because I can't show with advertising that that is related to sales. So, step 1, state the hypothesis. Step 2, let's calculate our test statistic. Well, previously we've calculated s squared sub epsilon as 0.3667. Remember, that also has the name of MSE as well. And we need to find the sum of the x's minus their corresponding sample mean squared. So 1 minus the sample mean, which is 3, that would be -2. Square it, you get 4. You do that throughout the data set, add them up, you get 10. Then let's plug in all the corresponding quantities into our test statistic. We have found beta hat 1 to be 0.7 before, and our test statistic is now about 3.66. Critical value, well, we go to our t distribution. Again, we can use the QT function to do that, to find this quantile from the t distribution, and we get plus or minus 3.182. So step 4, let's graph everything out. And notice that 3.6 is in this area that would be very unusual to have a test statistic value if the null hypothesis was true. So therefore we say, well, since this test statistic is so big, let's reject the null hypothesis. What does this mean in terms of the original problem? Well, there is sufficient evidence to show that advertising is linearly related to sales. Okay. So now let's look at high school and college GPA, that problem again. And it would be of interest, especially let's say if you're in the college admissions office and you need to make admissions decisions. You would like to know, is high school GPA linearly related to college GPA? And so with our sample, we can investigate if that is true or not. So from earlier, we estimated the model, put the results into mod.fit. Then when we say summary mod.fit, we got some output. We've seen before that beta hat 1 is 0.6125. Now what we have here in the std.error column, or in other words standard error, what we have there is the square root of the estimated variance of beta hat 1. Again, the phrase standard error is just another way that people refer to the square root of the estimated variance of a statistic. Okay? Then, if we were to take 0.6125, divide by 0.1237, we will get 4.953, and that's our t-test statistic value. So that's why it's called t-value for that column. And then this PR part right there, that stands for probability, and that's going to calculate the p-value. So the probability that a random variable t with the correct degrees of freedom is greater than the absolute value of 0.6125 is equal to 0.000103. That's our p-value. So that p-value is extremely small. And so again, what that says is that if the null hypothesis was true, this would be very unlikely to occur to get a test statistic like this. And so because of that, we would want to reject HO. Now, to get a confidence interval for beta 1, we can simply use the confidence function. The confidence function is actually a generic function using terminology that we've seen before. And what's actually executed is confident.lm. That's the method function that does these computations. And if you put in your object from the estimating the model, and then state what confidence level you want to use with the confidence interval, say 95%, we get a confidence interval of 0.35 is less than beta 1 is less than 0.87. That's our confidence interval, 95% confidence interval. So let's do the hypothesis test here. You know, typically the easiest way to do a hypothesis test once you have computer output like this is to use the p-value. So I state the hypotheses. I state my p-value. I state alpha, and then I say, because my p-value is less than alpha, reject HO. What does this mean in terms of the original problem? Well, there is sufficient evidence to show that high school GPA is linearly related to college GPA. Okay. So next here, I have a little segment here illustrating how to actually interpret this p-value, just kind of as a reminder. This is the same interpretation that we have seen previously. Please read this on your own and ask questions if you have them. Also, we should think about this scatter plot that we've calculated before. Let's see if I have the scatter plot up. Yes, I do. And, you know, what we're seeing here makes sense. That, yeah, if I just look at the scatter plot of the data, it looks like there is an upward trend there. And so I would expect if I were to put a line through the middle of these points, I would expect to have a positive slope. And this evidence is so overwhelming from this sample of just 20 people, we can actually then conclude that indeed, truly, in the population, there is this linear relationship. Of course, though, we are setting a particular probability for a type 1 error too. So that gives us some level of confidence of how good our statement is. Okay, so let's look at another example. Continuing with the college GPA example, rather than using high school GPA, how about we use instead the number of times that a freshman eats pizza during their freshman year as our independent variable. And we try to use pizza consumption as a way to predict college GPA. Now, we would expect that there isn't a linear relationship between the two. And that's the point of me making up this particular problem. So the actual data itself is in collegegpapizza.csv. I read it. So one particular student, same first student that was in our previous data set. One student ate pizza only twice, and they had a college GPA of 3.1. The next student ate pizza 9 times, and they had a college GPA of 2.3. Okay, so let's go ahead and estimate the model. Remember, we use the LM function. We're going to put college.gpa again as the response or dependent variable. And we're going to say that college GPA is going to, or what causes it to vary is due to pizza consumption. Data is an object called GPA2. I summarize the model fit. This is what I get. So my beta hat 1 is negative 0.0165. Note that we are now on page 9. And from this, I could write out my model as y hat is equal to 2.94 minus 0.0165 times x, where x is pizza consumption. My test statistic value is negative 0.461. My p-value, wow, 0.651. That's pretty large. So what that is telling you then is that if indeed the null hypothesis was true, that there was no relationship, since this probability is so large, that tells you, hey, this test statistic, observing this estimate, would not be unusual. It would be reasonable to have that if the null hypothesis was actually true. We could look at a plot of the data as well. Here's our plot. So the circles are the plotting points, the observed values. The red line is the estimated regression model. And we can see that as the times you eat pizza increases, my college GPA, there's not much change at all. So that's why that p-value was so large. One could go formally through the hypothesis test, and I did here. So the formal conclusion would be, based upon the sample, there is not sufficient evidence to show that the number of times a student ate pizza during their freshman year is linearly related to college GPA. Okay. So we talked about making inferences about beta 1. You might be wondering, well, what about beta 0? Well, rarely is that of interest. And so I'm going to not talk about that here. The only possible time where that might be of interest is that, let's say in your data set, x equals 0 is meaningful. Well, why in that particular case? Well, remember, beta 0 represents the y-intercept of our model. And so when x is equal to 0, the expected value of y would be equal to beta 0. That's the only time it would be of interest. And very, very rarely have I ever seen it in actual application of it be of interest. So it's not really worth our time. But what is definitely worth our time is to make inferences now about the expected value of y. So, we can get a y hat from our sample regression model, and it doesn't really say anything about how good that estimate is. But what you would like to be able to do, since y hat's trying to estimate the expected value of y, is use this y hat to, let's say, come up with an interval estimate for the expected value of y at a particular value of x, so that you can say with 95% confidence that the average value of y for a particular x is between, let's say, two different numbers. And that's what we're going to do here by forming a confidence interval for it. Okay. Now, often textbooks do the following when they explain it. They will say, okay, so we're interested in a particular value of x, maybe like with the high school and college GPA example, maybe for students, all students who have a high school GPA of 3.0. And while 3.0 may be in my data set, it may not be as well. So as a way to differentiate it from the actual observed data itself, often textbooks will do something like this. They'll put x with a subscript of something there to say, hey, this is a potentially a new value or a different value. It doesn't have to be in the data set. And I decided to use here x sub h. I'm not for sure why I chose h, other than h comes before I, and we often use I as our index to represent particular things. So let's say x sub h is equal to 3.0. I want to find a confidence interval for what the, let's say, expected college GPA would be for all students who would be at a particular university, given having a high school GPA of 3.0. What would be the average value of the corresponding college GPA? And so the way to do that, we follow a very similar pattern to what we just got done doing. We take the estimate of what we're after. In this case, we're after expected value of y. We can estimate it with y hat. So we take y hat sub h, and we subtract off what the expected value of y hat sub h would be, and we divide by the square root of the estimated variance. That's why, again, I have the hat there. The estimated variance of y hat sub h. Should look familiar based upon what we just got done talking about with respect to beta hat 1. Now, this quantity here has a t-distribution with n minus 2 degrees of freedom with it. What is this estimated variance? Again, in a mathematical statistics course, you would go through the process of deriving that. In the end, it becomes this. This is all that you need to know. S squared sub epsilon. So in other words, our mean square error times the quantity 1 over your sample size plus, then in the numerator, we take our corresponding x value, like 3.0, subtract off the mean of all the x values, and we square it. And we take it divided by the sum of all the x minus x bar squared values. Okay? So that's the estimated variance. Then we can now make probability statements about this because this is a random variable. And since we know its distribution, guess what we do? We put the random variable value in the middle. We find corresponding quantiles from its distribution, t-distribution in this case. We find these quantiles in a way so the corresponding probability is just 1 minus alpha. Then we rearrange some terms using algebra so that we have what we're really after in the middle, the expected value of y sub h. And on the sides, we have our random variable y hat sub h. So you can think of, again, this y hat as being an actual random variable because it's going to vary from sample to sample to sample depending upon what the beta hat zeros, the beta hat ones are from one sample to the next. We subtract off the quantile from the t-distribution. We take it times the square root of the estimated variance. And then on the right side, exactly the same thing, but you have a plus there. Then I take this stuff all out of my probability statement, and then I replace the random variables with their corresponding observed values. So now notice how I have a little y hat sub h there. And this is our interval. 1 minus alpha times 100% confidence interval for the expected value of y sub h. So let's go ahead and look at how we can do the calculation. Let me actually jump on over here to 10. Okay, so what should I use for x of h? Well, it depends upon what you're interested in. Let's say I'm interested in high school GPAs of 2.0, 3.0, and 4.0. So what I'm going to do is construct a data frame where I use the exact same variable name for my high school GPA as I have in my original data set. This is extremely important that you do that. So we use a capital HS dot capital GPA. You have to use the exact same name. And what I'm going to do is give it 3 different values. So I'm going to combine together 2, 3, and 4. Put this all in an object called more.gpa, for lack of a better name. And so now I've formed a new data frame with these 3 elements. Then, to find the confidence interval, I use a function called predict. Predict is a generic function in R. What actually ends up being executed is predict.ll. And for its first argument, which is called object, I'm going to put in mod.fit, my results from estimating the regression model. And then they have an argument called new data that says, essentially, what are your x's? What are you interested in estimating at? Well, high school GPAs of 2, 3, and 4. So new data, it gets this new data frame that I just formed. And also we have this se.fit argument, and I have true there. What that's going to give me is this square root of the estimated variance of y hat sub h. I have interval equal, I want a confidence interval. You might be wondering, why do I have to specify it? Well, very shortly we're going to learn about another kind of interval called a prediction interval. That's why. And then I want a 95% interval. So if I go ahead and execute that code, this is what we get. And I have that already in Word, so let me just use that instead. So this fit part here corresponds to y hat sub h. So the estimated college GPA for students with a high school GPA of 2.0, the estimated college GPA is 2.31. Then we have lower limit, upper limit for the confidence interval. So when x is equal to 3.0, then the confidence interval, 95% confidence interval for the expected college GPA, what I would expect on average for those students is 2.03 to 2.60. Now I have that for all 3 different values that I had in my more.gpa data frame. Here's the se.fit once again, the square root of the estimated variance of y hat sub h. Residual.scale, for some reason they use that name there, and what that is s sub epsilon, the square root of MSE. Okay. So that's confidence intervals for the expected value of y sub h. Now, you may also be interested in not a confidence interval for the expected value of y sub h, but rather instead, could I somehow predict y sub h itself? So for a particular student, what would their college GPA be relative to our example? So notice the difference here. The expected value of y sub h is actually a constant. It's essentially the average of all possible students, again, relating to the GPA example. Average of all possible students, their college GPA in the population that had an x equal to, let's say, 3.0. Here, now what we're trying to do is we're trying to predict essentially one person's GPA, and that obviously now is a random variable because it can vary from one person to the next with that same x value, that same high school GPA. And so because of that then, it's going to be harder to form an interval for it and have the same confidence level as what we would have for a regular old confidence interval like what we just formed for the expected value of y. And so to take that into account then, The interval that we're going to form here is going to be wider to take into account that extra variability that now we're working for an interval with a particular random variable. Since this is an interval for a random variable itself, it actually has a different name. It's referred to as a prediction interval, or PI for short. So again, the difference can be seen with this plot here. So when we were forming a confidence interval for the expected value of y, basically what we were trying to do, excuse me, is capture that red line inside our interval. Now with a prediction interval, we're trying to capture these green dots. And you can see these green dots move around a lot more than simply a straight line. And so that's why this is a more difficult problem, and that's why we have a larger variance that we're going to be working with when we form our interval estimate. Okay, so the process that we're going to follow is very similar to what we've seen before. Before we had y hat sub h minus expected value of y. Well, we're going to take that expected value out, and so now this numerator itself, the whole thing, is a random variable. Y hat sub h is a random variable. Y sub h is a random variable. And since they're both random variables, then in the denominator, we're going to find the estimated variance, or the square root of the estimated variance, of now the whole quantity that's up there. This has a t distribution with n minus 2 degrees of freedom still. But this estimated variance, what's interesting is this. Exactly the same as before, but now we have a little bit more. So before, we only had the part that I'm circling right now. But with this y sub h, now we have this extra part that we're going to deal with. And mathematically, what ends up turning out to happen is now I have an extra 1 with inside the parentheses. So we can see that this estimated variance as the denominator is going to have to be larger than what we had previously when we were dealing with expected value of y. So I have this quantity that has this t distribution. So what I'm going to do is I'm going to find corresponding quantiles chosen in a way from this distribution such that the probability of everything inside there, that inequality, has a probability of 1 minus alpha. Then we rearrange some terms in our probability statement so that we get what we're interested in now in the middle of this inequality. And then when we take stuff out of that probability, we turn the random variables now into their observed values that we get from our sample. And here is the 1 minus alpha times 100% prediction interval for y sub h. Okay, let's take a look at now the example. So once again, I can use the predict function with the high school and college GPA to find my interval of interest. Everything remains exactly the same, except for now I say prediction instead of confidence. So let's go ahead and run that. And this is what we get. So again, we have y hat there. Now my prediction interval, when x is equal to 2, my 95% prediction interval is 1.54 up to 3.09. Notice how that is wider than what we had before. And it's all essentially because of that variance equation that we saw. And you can look at all the other intervals from when x is equal to 3, when x is equal to 4. Indeed, again, we get wider intervals. Now, do note the output here, the rest of the output is exactly the same as what we had above. In particular, and I think this is somewhat misleading, is this se.fit. What that se.fit is, notice how it's exactly the same as before. So it's giving you that same variance that we were using with the confidence interval, not the variance now that we're using with the prediction interval. So please be aware of that. Okay. Now, a very useful plot that you often see in situations like this when you want to find interval estimates for the expected value of y or y itself is to summarize all possible confidence intervals that could be formed, all possible prediction intervals that could be formed on a scatter plot with that sample regression model plotted. Here's what the plot looks like. So we have high school GPA on the x-axis. We have college GPA on the y-axis. The circles there are our observed values from our sample. The red line is the sample regression model or estimated regression model. And then the green dotted, or I'm sorry, green dashed lines there, those are what are called confidence interval bands for the expected value of y. So for example, at x equal 2, if I go all the way up to where I hit the line and come all the way over, what we have there is that bottom bound of 2.03 that we saw for a confidence interval for the expected value of y when x was equal to 2. And if we keep on projecting up and we go over, we see the upper bound of that interval, which is 2.60. We can do the same thing with the prediction interval. So there's the bottom bound, which was calculated to be 1.54, and the upper bound, which was 3.09. So what this plot gives you is that for any particular value of x, you can see what the corresponding confidence interval or prediction interval will be. Again, these green dashes are called confidence interval bands. I think I failed to mention this. The blue dashes there, that's for the prediction intervals. And these are prediction interval bands. A cool plot to look at. Now, how do we get this cool plot then? Well, to see how we get it, then, let's take a look at some other ways to use the predict function first. Let's say I just want to get y hat itself only from using the predict function. So the way to do that is say predict object equal mod.fit, and then our new data again. And let's say I just want it at a high school GPA of 2.0. So what I can do is for my data frame right inside the predict function itself. And so that when I do that and save the results into, let's say, save.pred1, pred for predict, this is what I get, 2.31. Okay. Let's use that now to our benefit to do this plot. So first of all, I'm going to get the scatter plot. Okay, let's go ahead and do that. So there's the scatter plot of my data. Now I want to plot then the estimated regression model or sample regression model on it. The way that we've done that before was we use the curve function. And then in EXPR, what do? Well, we take mod.fit. $coefficients. I want to take the first element out of coefficients because remember that's going to be my beta hat 0 plus mod.fit $, if I can type, coefficients, bracket 2 end bracket to give me my beta hat 1 times x. That's the way we've done it before. Here's another way you can do it. Use the predict function. So predict object equal mod.fit, just like what I did here. New data equal, I form my data frame inside my predict function, just like what I did here. But now the difference is instead of putting a 2 there, I could put something else. How about we just simply put x? And so what R is going to do then when it does the curve function, it's going to put in a whole bunch of x's. It's going to evaluate the model, and then it's going to produce the corresponding plot. Where the line is going to be red is going to be a solid line, line width equal 1, which is the default, added to the current plot, and then here's my range that I want to get the line at, again, the minimum to the maximum possible x value. So if I go ahead and do that and see the plot, voila, there is my regression model plotted. Okay, now let's talk about those confidence interval bands. So here's another way that we could have used predict. Predict, object equal mod.fit, new data equal, and again, I just put in one particular high school GPA that I'm interested in. Again, I need to put it in terms of the data frame format. Then I say interval equal confidence, level equal 95%, 0.95. Put that into an object called save.pred2, and there we go. So notice what I got here. I didn't get those se.fit values. I did not get the residual.scale value at all. I did not get the degrees of freedom at all. All I got back was y hat and also the lower bound and upper bound of the interval when x was equal to 2. And let's say I want this particular value there. Well, the way that R stores this information is what's called a matrix. And what I can do is say I want the second column of the matrix. And we've kind of seen this kind of notation before when we were first looking at data frames in the past, where I could specify a whole column by specifying the column number. Here, this is column 2. And notice I got that out. If I did 1, 2, that would also work too. Row 1, column 2. But you could do either or. They both would work for this case. So taking that into account then, let's now use the curve function to get the lower bound or lower band plotted on our plot. So predict object equal mod dot new data equal data dot frame high school dot GPA equal x, just like what we just did up here. Interval equal confidence, level equal 95%. And then I have this code right there, and we might not have seen this yet. Basically what I'm doing is, let's not save the results into an object. Let's immediately take out that second column. Let's actually do that up here first, just to emphasize the point. So this is the exact same code that we saw here. But instead of saving it into an object, I'm going to immediately extract that second column out. And there we go. So when I combine that then with the curve function here, I'm going to immediately take out that second value. And then on the rest of the part of my plot, I'm going to plot the line with dark green. It's going to be a dashed line. Line thickness of, or line width thickness is 1, added to the current plot. And then my x-axis limits correspond to the minimum and maximum college GPA. Let's go ahead and run that, see what happens. Now I got my bottom band. Okay, I can do exactly the same thing with the upper band by saying comma 3, because the third element was the upper limit for that confidence interval. So let me go ahead and do that as well. Take a look at the plot. There we go. Let's do the prediction interval bands. Exactly the same thing, but now I say prediction instead. Okay. Oops. And there's our plot. Let's put a nice little legend on the plot too. And to do that, I'm going to use a function called legend, where the names of things in the legend corresponds to the legend argument. So legend equal, I'm going to combine together the phrase sample model, 95% confidence interval, 95% prediction interval. Combine that together. The sample model, the color of it's going to be red. The color for the confidence interval band was dark green. And I failed to mention this before, for the prediction interval, it was blue. Okay. What are the line types that we saw in that plot? Well, for the actual model itself, it was solid. For the confidence interval, it was dashed, as was also the prediction interval. BTY says box type. Do you want to put a box around the legend? Nah, we don't need it. So equal no, or equal quote and end quote for no. And then CEX equal 0.75 means the text itself is going to be 75% as big as the default. Lastly, then, this locator 1 that we have right here at the beginning. This is an interesting way in R where you can actually click on the plot to drop the location of the legend in. So if I run this, the plot comes up, and look at what my mouse looks like. It's a plus sign because it wants me to left click on the plot to add the legend to it. So let's say I want to add it right there. So I left click, and there we go. kind of a cool thing that you can do. Okay, so in the end, this is kind of a complicated plot to construct, but it's really, in the end, I don't think really too bad once you get the hang of how to use the curve function with the predict function itself. So that's the end then of this section about inferences regarding our regression model. We can do inferences about beta 1. We can do inferences about expected value of y. We can do inferences about y itself. A very, very useful subsection when we're talking about regression analysis.